So, we have been talking about superalloys last class, and superalloys we mentioned that the major high temperature strength in superalloys comes from two aspects. One is the precipitates that you are putting in, the gamma prime, Ni3Al mostly, and some carbides of course, and secondly the oxide dispersides that we are putting in. We all know usually that any time you have a precipitate has an inherent problem. What is the inherent problem? The problem is that it dissolves at high temperatures, because the precipitate has come from the matrix. As long as it has come from the matrix, anything that comes out of something has to go back into it. So, provided you provide that temperature and pressure that is necessary and the time that is necessary for it to dissolve back. So, if you heat this precipitate, the alloy at higher temperatures for a long period, these precipitates either coarsen or dissolve. So, as a result, most of the alloys where precipitation hardening is used as a main strengthening mechanism cannot be really used at higher temperature. That is where people tend to use, particularly for high temperature application, particles which do not dissolve back into the matrix. Those are what we call dispersoids. Just to differentiate between precipitates, we call them as dispersoids, but basically the more or less the strengthening mechanisms are similar, excepting that dispersoids are never coherent or semi coherent. They are always incoherent, because they are something which has come from outside, they are externally added, isn't it? So, they have not been generated from the matrix. So, as a result they are usually incoherent, and incoherent precipitates do not give you high strengthening at the nominal temperature, at the low temperature, or at ambient temperature I should say. So, you use them for high temperature applications only, but not really for low temperature application. And this kind of materials where you add dispersoids intentionally have been called from time immemorial that they are what are called composites. We have a number of these composites. We basically classify these composites as metal matrix, the ceramic matrix, and the polymer matrix based on the matrix. One can also classify them depending on the reinforcement that we are using. There are different types of composites: particulate composites, fiber reinforced composites, discontinuous reinforced composites, or continuous reinforced composites, depending on whether the fibers that we are using are short fibers or long fibers, whether they are continuous from one end of the component to the other end, or they are existing as randomly distributed fiber kind of reinforcements in a matrix. So, depending on whether you are looking from the matrix point of view or the reinforcement point of view, one can talk of a number of composites. But many of these composites, particularly if you look at the metal matrix, which as metallurgists we are more interested in, if you look at these metal matrix composites, most of the composites traditionally which are made are those where the reinforcement is added externally. That means, we take a liquid metal or an alloy, add the reinforcement particles or any other morphology, whatever it is, whether it is raw, the wires or the fibers of these, or fine spherical particles, or whatever may be the shape of the shape and morphology of these particles, we add them externally. And the most common example of that is the aluminum silicon carbide, which is very famous. Most of the components nowadays, even for example some of the engine blocks, people are trying to make these with aluminum silicon carbide composites, but there are problems with this. What are these problems? If you try to understand, before we go to that, let us see how we make composites. Composites are made by a number of routes, starting from what is called powder metallurgy. You can take the matrix, powders of matrix and the powders of the reinforcement and then mix them together, sinter them together, and you have a composite. And nowadays people also do it in a finer scale, what are called nano composites. In a similar way, you make nano composites by mechanical alloying, again compact them or sinter them. Either whether you generate these particles in situ inside the matrix during mechanical alloying, or take a matrix powder and the reinforcement powder, ball mill them together to make them finer and then compact it and sinter them. This is all basically a solid state processing route. Broadly one can call it as solid state processing route, whether it is a conventional powder metallurgy route or the recently developed new techniques such as high energy ball milling techniques. So in all these techniques, basically you start with powders. The other technique is what is called spray deposition. Here also you basically generate powders, but from the liquids. So in a spray deposition, what you do is you melt the whole alloy, put these particles in that liquid metal and then spray this liquid containing these reinforcement particles as droplets, and let these liquid droplets condense on some substrate and then generate whatever component that you are interested in. This is what is called spray deposition. A number of people are working on such things, and the other thing is called compo casting, or this is also called stir casting. Stir casting technique is basically you again take the liquid metal, add these particles, the reinforcement particles to it, stir the liquid so that they are uniformly homogeneously distributed, and then pour this slurry into a mold and then generate a casting out of it, and that casting would be a composite casting. So this is what is called compo casting. That means you are casting a composite. That is why it is called compo casting, or people also usually call it as stir casting, because you need to stir for the uniform distribution of that. We will come to it, what kind of problems that we face with this kind of methods. The other method which has become popular is called infiltration technique. The infiltration technique basically comes because of the disadvantages in this compo casting. What are the disadvantages? The basic disadvantage is the wettability of the particles with the liquid. Many times when you have added externally these reinforcement particles to the liquid metal, not every particle has good wettability with the liquid. That means that surface energy, the interfacial energy of the particle with the liquid is not compatible in such a way that you do not get good wetting. If the wetting is not good, the composite that you are making will have two problems. One is that if the particles are not wetted by the liquid, all the particles get segregated and then either they float or sink in the liquid depending on their densities, or even if they are suspended in the liquid, they will get segregated to certain regions, and then what you generate is a casting which will have inhomogeneous distribution of these particles and then clustering or agglomeration of these reinforcement particles in some regions, so that you do not have uniform distribution. So that is one problem. Second problem is, if the wetting is not good, the interface between the particle and the matrix is not going to be very good, and because of that the load transfer when you use these components in service is not going to be good, and because of which you do not get whatever strength levels that you are expecting. Usually whenever we add a reinforcement to the matrix, we expect the strength to increase, and we usually use a formula something like this: sigma yield stress of a composite is given by sigma yield stress of the matrix multiplied by the volume fraction of the matrix plus the sigma yield stress of the reinforcement multiplied by the volume fraction of the reinforcement. This is what is called rule of mixtures, which is not valid in all cases. Okay, under ideal conditions one can use this kind of a thing, and there can be possibilities, and in fact in reality many times the composite strength does not exactly conform to this particular equation, but is either higher or lower depending on again the interface strength. If the interface is good, if there is a compatibility between the reinforcement particle and the matrix at the interface, then more or less the load transfer is very smooth across the interface, and hence one can use this kind of an expression very easily. And hence, as you can see that when compared to a normal pure metal, when you add a reinforcement particle, because the yield strength of a reinforcement particles are much higher, because they are all ceramics, their strength levels are very high. So, as a result the strength of the composite is going to be higher. So, this is what we expect. So, but that is possible only when you have a good cohesion at the interface, and most of the time the particles that we add do not have good cohesion at the interface, and if that is the case, then the stir casting technique is not a good answer to make such composites, because when you try to stir to have a uniform distribution, still if the particle does not get wetted by the liquid, whatever stirring that you do is of not much of a use. So, that is why the infiltration has an advantage. Basically here what you do is you take the reinforcement particles in a tube like this in the form of a preform, all the reinforcement particles inside this, and then pour the liquid from top and try to suck this liquid through this preform using some vacuum pumps. Let us say there are different types of infiltration, pressure infiltration, pressureless infiltration. For example, if you just pour liquid metal on top of this, because of the gravity also the liquid tries to go through this preform, so called preform, and if you have the preform basically containing these silicon carbide particles, there are certain pores in the preform, and the liquid goes through that pores, and finally what you end up is a composite where all the pores in the preform are filled with the liquid metal. So, you will have the liquid metal engulfing all these particles, so that you have ultimately a microstructure like this. You have particles and the matrix alloy surrounds all those particles. This kind of a composite you can achieve more or less uniform distribution of these particles, because here the liquid is passing through the whole preform. If within your preform, if the particles are uniformly distributed, which anyway is guaranteed, because you have taken powder particles, compacted the powder particles, made a preform. Only problem is here the volume fraction of the reinforcement particles is going to be much higher than a typical composite. In a normal aluminum silicon carbide composite, the usual volume fraction of the reinforcement that we add is of the order of 20 to 30%. Nobody adds more than that. Whereas here, if you can imagine, you imagine a kind of a close packed spheres. If you imagine close packed spheres of these particles, silicon carbide particles, if you assume them to be spherical balls, if they are closely packed, and if you have a preform which is close packed, what is the extent of porosity that is left out? 26% to be exact, because close packing, the packing factor is 74%. We know it from our second year BTech level. So, 26% is the one. So, you will have 26% of matrix and 74% of reinforcement in principle if it is a close packing. So, how do we solve this problem? And if it is going to be like that, you have more volume fraction of the reinforcement, definitely the composite that you are going to make is going to be brittle. So, you are not going to get the advantage of having a metal matrix composite. Why do we make a metal matrix composite? So that we can gain the advantage of the metal matrix which is the ductile. So, we want the composite to be both strong and ductile, and that is why we go in for metal matrix composites and not for ceramic matrix composites or ceramics. So, the advantage of having metal is lost if you have that kind of volume fraction. So, there are techniques where people try to reduce this volume fraction. Can you suggest some ways how one can reduce this volume fraction of silicon carbide by using this kind of a technique? Do not change the technique of infiltration. If you want to use infiltration technique and still have lower volume fraction of the reinforcement, what do?
You can charge this particle and special the particles separated.
How do you separate the distance between the particles?
By charging
Electrolytic charging, as any other techniques? Isostatic pressing, no, if you do isostatic pressing they will come closer.
Sir, loose powder sintering?
Loose powder sintering, okay. There are also methods by which you add some binding agents which have a tendency to evaporate the moment the liquid metal comes in contact, which have a lower boiling point. So, you add such volatile matter while compacting or while mixing the powders and then compacting, so that you fill up the whole thing with some of those low boiling volatile matters, so that the moment liquid metal comes in contact it is lost, so that those voids that are left out are filled by the liquid metal. There are also methods like that. So, the basic advantage with this is, yes, with this kind of methods one can control the volume fraction, but more important is one can achieve uniform distribution of particles without any segregation. But there are limitations with this also. One cannot produce very intricate castings. Usually infiltration is feasible if the shape of your casting or shape of the preform which is being infiltrated, if it is very simple such as a cylinder or something like that. If it is a very intricate casting, then infiltration becomes more difficult. So, but one can produce, let us say, rods and further deform them for any shape of our interest if you want to achieve various shapes from that, let us say rods or or even people are interested in slabs or plates, if you are interested in like that. So, this is one possibility. So, there are limitations with this technique, but at the same time one can achieve the more uniform distribution. Another problem that comes with stir casting is that the liquid metal has a tendency to react with these particles in a number of cases. For example, if you take aluminum and put silicon carbide into it, there is a tendency for the silicon carbide to react with aluminum and form Al4C3 compound, plus some silicon comes out.
Sir, is this a problem in star casting or in infiltration?
This is the problem in stir casting, which can be controlled in infiltration, because in infiltration the time of contact is very short. What we are doing is just pouring the liquid metal and then sucking it using some vacuum pumps, let us say. If you want to decrease the time of contact, the best thing is to use vacuum sucking rather than gravity infiltration. If you use gravity infiltration, the time required for infiltration is very long. So, instead of that, if one can use pressure gradients to suck the liquid metal through the preform, one can achieve it very fast. So, because of this, I do not say that this problem does not exist in the infiltration, but it can be controlled because the time of contact is very short. In a normal stir casting route, one has to hold the liquid metal for a long period along with the particles, because of which you can have more reaction. So, that is why one goes for infiltration, but as I told you, infiltration itself has limitations, and because of which a new techniques have come up which are called in-situ techniques. So, in in-situ processes, what we do is we generate these particles in situ. We will go in detail about this. Before that, let us look at once again what are the problems of normal MMCs, conventional MMCs. One is the poor cohesion at the particle matrix interface, which we have talked about, and in case of in situ MMCs we have a much better clean interface. Why? Because here the particle is coming out of the liquid, the particle is not externally added. This is where we differentiate between these composites. One is called ex-situ composites, another is called the in-situ composites. Ex-situ composites are those where the reinforcement is externally added. In-situ composites are those where reinforcement is generated in situ. Then you can say even precipitation hardening is also something like an in-situ composite. Why don't we call that as an in-situ composite? The only difference here is that in precipitation hardening, the precipitates form in the solid state from a supersaturated solid solution, whereas here in the in-situ composites, the particles are coming from the liquid because of the reaction of this liquid with something else. It is not that liquid is a supersaturated solid solution from which it is coming. So, the liquid is allowed to react with certain materials, and the reaction products are these reinforcement particles which get uniformly distributed in the liquid. And now, if you take this liquid containing these reinforcement particles and then pour it into a mold, you generate the required casting, and that is what is the in situ MMCs. So, in situ MMCs are basically generated in the liquid state, whereas the normal precipitation hardening is usually in a solid state, and these are formed by chemical reactions, as I told you, and a number of applications where people have already started using these in situ composites, such as automobile, and we also have helicopter blade sleeves. These are just a few examples. I do not say that this is the complete list, and the cylinder liners in the automobiles, the seat tracks, wherever you need high wear resistance and a high strength combination is where we use these in situ composites. And what kind of advantages you have? A number of them. First of all, these particles are stable because they are coming from the liquid state. So, unless you take the whole composite up to the liquid state, they do not dissolve back. Unlike precipitation hardening, the particles do not dissolve back into the matrix. So, they are thermodynamically stable reinforcements, and as a result there is less coarsening. The tendency for coarsening of these particles or dissolution at high temperatures is very low, because of which one can use these composites at high temperatures very easily. In addition, the reinforcement matrix interface is very clean, and because of which you have a strong interfacial bonding. You have a strong bonding because of the clean interface, because there is no what is called the reaction products formation in these cases, because the particles are themselves coming from the liquid metal. As a result, there is no reaction between the particle and the matrix itself. So, as a result you have a clean interface, and one can control the fineness of the reinforcement particles by controlling the time and temperature at which these particles are coming out, because in a case of a ex situ composites, the size is only controlled by the external particle size, whatever particle size that you are adding. And in fact, there is a problem when you come to infiltration, one cannot use very fine particles. If you use very fine particles, then you can see that the pore size becomes so fine, then the infiltration becomes very difficult. So some of the techniques such as infiltration are suitable only when you want to use larger size of particles. Otherwise, if you want to use very fine size, it is difficult. So fineness can be really controlled in this case, and one can achieve uniform distributions, and once you have uniform distribution, you can have uniform mechanical properties. This is one very important thing in case of composites. If you do not have uniform properties, then the crack can initiate at any particular place where there is a lot of agglomerates of these reinforcement particles, and then the crack can propagate. So as a result, we do not want any agglomeration of particles or segregation of particles at some region. We want a uniform distribution so that the material can achieve high strengths.
But sir, some segregation must be in the liquid state.
If there is a segregation in the liquid state, that is the segregation. See, this reaction, once there is a reaction of, we will come to those things. Once there is a reaction of certain chemical with the liquid, there is some particles come out because of the reaction product, and some of this reaction product get dispersed in the liquid, and some of them because of their low density get floated and go into what is called the dross or the slag. So we will talk about those things whenever we talk about the reactions. So definitely you will have much more uniform distribution than what you achieve in the external in-situ composites. And another thing is, so this conventional processing with the potential for lower cost and production with a conventional equipment. That means one can use the normal conventional equipment itself. You do not need any special tools. For example, in-situ composites can be just melted in a normal furnace and then pour into any mold of any particular intricate shape, and then generate the casting of a particular shape that you are interested. So you do not need to have any additional capital cost than what you have in case of the typical conventional stir casting route. In fact, in case of stir casting, you need to have a stirrer. In this case of in-situ composites, most of these reactions are exothermic in nature, because of which you do not need any stirring. Automatically there is a lot of stirring that goes on because of these exothermic reactions. So these are some of the advantages of these in-situ composites. And we will today look at two types of in-situ composites. One is aluminum TiB2 in-situ composites, another is aluminum TiC in-situ composites. There is a lot of work going on nowadays on aluminum based in-situ composites, because people want some alternative for aluminum silicon carbide, because aluminum silicon carbide we know that there are problems because of two things. One is the reaction that we have talked about, the formation of Al4C3. Second is the lack of compatibility of the particle with the liquid, because of which you do not have good cohesion at the interface. People tried to overcome this by two ways. One is to modify the particle. For example, you take silicon carbide particle and then coat it with various metals such as nickel, copper, by electroless coating or electroplating kind of techniques. We cannot use normal electroplating because the particles themselves are not conducting in nature. So as a result, you have to use other methods such as electroless coating techniques, where people coat nickel, copper and other elements, and now once you take these coated silicon carbide particles and put it into an aluminum matrix, aluminum liquid matrix comes in contact not directly with the silicon carbide particle, but with this coating. So as a result, the metal-metal bonding is much stronger. So as a result, there can be a better cohesion between the particle and the matrix. So this is one possibility where the reinforcement particle is modified. Other possibility also is to oxidize silicon carbide. A number of people have taken silicon carbide particles and oxidized the silicon carbide particles, and once you oxidize it, you develop a surface oxide coating, and an oxide, silicon oxide, has a better wetting with aluminum than silicon carbide itself. So as a result, you can have slightly better cohesion at the interface. So this is another route people have tried, both of these are basically manipulating the particles. People also tried to manipulate the matrix. How do we manipulate the matrix? By adding certain alloying elements which can improve the cohesion. So, whenever we talk of a cohesion, basically it is the interfacial energies that are important. When you think of a liquid and a particle inside, what is important is the interfacial energy between the particle and the matrix. So, gamma LP or gamma LP, gamma liquid particle interfacial energy, and this gamma liquid particle interfacial energy depends on what is the composition of the liquid obviously, and also what is the nature of this particle. So, as a result, if either one can modify this particle or modify the matrix, so that one can have a better interfacial energy and have a better cohesion at the interface. So, people, for example, people know that if you can take aluminum, add some magnesium to it or add some silicon to it, silicon carbide is more coherent or more compatible with aluminum silicon matrix or aluminum magnesium matrix than the pure aluminum itself. This is one of the experimental observations a lot of people have made, and so nowadays people try to not make aluminum silicon carbide composites with pure aluminum itself, and then instead of that people try to make aluminum magnesium aluminum silicon alloys and then add silicon carbide. This is one reason. Second reason is that the reaction of aluminum with silicon carbide, this decreases if you have silicon already inside in the aluminum. If you take an aluminum silicon alloy melt and then put silicon carbide particles into it, the reactivity of silicon carbide with aluminum silicon matrix is going to be much lower than the reactivity of silicon carbide with aluminum. So, that is another reason why. So, the reaction between these two particles and the matrix is also decreased when you add silicon to that. The reason basically is that when you take a pure aluminum, so the reaction of this two basically depends on the activity. When you have silicon in the aluminum, already there is some activity of silicon inside the aluminum. So, as a result, this reaction progressing in this direction gets reduced. So, because you see the reaction generates silicon. So, if you already have a silicon here, so the kinetics of this reaction gets hampered. So, as a result, this reaction will not occur so fast the way it occurs in a pure aluminum, because in a pure aluminum the moment silicon comes out, this silicon goes back into this aluminum. So, already there is silicon in this aluminum. So, as a result, you can see that this reaction does not progress. So, similarly, the magnesium, another thing people have observed is that when there is magnesium, it forms what is called a spinel. Do you know what is a spinel? What is its composition? AB2O4, fantastic, correct. It is a AB2O4 type of structure. What is this A and what is this B? It is AlMg2O4 with some silicon in it. So, what happens is the moment there is magnesium, this compound forms at the interface between the silicon carbide and the matrix, and then prevents the reaction of the silicon carbide with the matrix, and the formation of the brittle Al4C3 phase can be avoided. So, as a result, so magnesium helps in improving the wettability of the liquid with the silicon carbide. In addition, magnesium also has a tendency to change the surface tension of the liquid aluminum, so that the wettability can be further improved. So, there are two advantages of adding magnesium: one, the formation of the spinel, the change of the surface tension. So, because of this aluminum silicon carbide composites are still being worked out by making this kind of modifications of either the matrix or the reinforcement particles, so that one can generate still aluminum silicon carbide composites, but there is a lot of tendency to develop newer composites which are called the new generation composites, and two examples of that is aluminum TiB2 and aluminum TiC. We will try to see some results of this work people have been doing in this particular direction. If you look at aluminum TiB2, people have tried to make composites with pure aluminum as a matrix, aluminum copper as a matrix, or aluminum silicon as a matrix. The advantage of taking aluminum copper as a matrix is because you can have precipitation strengthening also in addition to the reinforcement particles that you are adding. So, one can have a combined effect of both the precipitates and the reinforcements. So, as a result, aluminum copper alloys, particularly aluminum 4 copper alloy, if you take it and add the TiB2 particles, one can have much better strengthening that one can achieve when compared to pure aluminum. Similarly, aluminum 7 silicon. In aluminum 7 silicon, we already know that silicon gives you strengthening. So, as a result, one can have additional strengthening because of that. And how do people make it? They again take a liquid aluminum in a crucible, add certain salts which react with this liquid aluminum and then generate the TiB2 particles. And if you want to improve the reaction, one can use stirring, but this is not essential because this reaction itself generates a lot of heat because of the exothermic nature of this reaction. What are these reactions? The reactions are like this. The salts that are usually used are two types of salts. One is called K2TiF6 and another is KBF4. If you carefully see, one has titanium in it, another has boron in it. So, you are adding two salts to liquid aluminum, one containing titanium, another containing boron, and when you add these two salts to aluminum, the reaction of these two salts with aluminum is vigorous and exothermic in nature, and that leads to the formation of TiB2 and gives some kind of a slag or a dross, which is nothing but KAlF4, and which can be separated from the liquid metal very easily. And this is one of the techniques which people use, which is called mixed salt route. That means, by adding the two salts together to the aluminum. Another possibility is what is called master alloy route. That means, you separately make aluminum titanium and aluminum boron master alloys. How? Take aluminum plus K2TiF6 and you take these two and react them together. The titanium that comes out of this reaction reacts with the liquid aluminum and forms Al3Ti, and the KlF4 comes out. Similarly, when you react aluminum with KBF4, the boron will react with aluminum and forms Alb2, and if you take these two master alloys and then remelt them together, what you see is that this Al3Ti reacts with the Alb2 at high temperatures, and you ultimately end up in TiB2. So, one can either use this technique or this technique. Only thing is, commercially this technique is more viable than this. Obviously, you can see here you have to melt it 3 times. 2 master alloys have to be made, and the 2 master alloys have to be remelted together to get this. So, as a result, this is a much better alternative, and the reactions are like this. If you look at it carefully, aluminum, when it reacts with KBF4, first thing that happens is the boron is rejected out of the KBF4 and goes and dissolves into liquid aluminum. and as the boron keeps on dissolving into liquid aluminum, once it crosses the solubility limit, in a liquid aluminum boron is soluble up to certain extent, it cannot dissolve to whatever extent that you want. So, there is certain solubility. Once the solubility is reached at that temperature, the AlB2 or AlB12 comes out depending on the temperature. At high temperature AlB12 comes out, at low temperatures AlB2 comes out. So, that is how you can make a aluminum boron master alloy. Another problem with this technique is that the KBF4 has a tendency to dissociate into Kf plus Bf3, where Bf3 is a gas, and this gas can escape out of the crucible. If it escapes out of the crucible, then all the boron is lost, because you can see here Kf does not contain any boron. So, only Bf3 contains boron. So, as a result, before this gas escapes out of the crucible, it has to react with the aluminum. If it does not react with the aluminum before it escapes, so you lose lot of boron. So, one has to control the process carefully, so that you do not have loss of boron. This is one problem with the aluminum KBF4. Then the second reaction, if you look at it, aluminum K2TiF6, here again the same process. First the reaction occurs and the titanium is released, and this titanium dissolves into aluminum, and once the solubility is crossed, you get the Al3Ti or TiAl3, and that is what is called an aluminum titanium master alloy, where you will have alpha aluminum, which is the matrix, and the Al3Ti particles, and this reaction is very vigorous and highly exothermic in nature, and very fast reaction this occurs. And if you look at the thermodynamics, according to the thermodynamics, the TiB2 is the most stable phase when compared to AlB2 or TiAl3. This TiB2 is the most stable phase. That means, if you have Al3Ti and AlB2 together at any given temperature, there is a possibility of these two reacting together and forming TiB2, because you can see the Ellingham diagram, which shows clearly that this TiB2 is much below than all these reactions. This is the top one is for the aluminum reacting with boron giving you AlB2, the next one is TiAl3 giving you TiAl. This happens at high titanium content, because we do not add that much titanium, so we do not go into this regime at all. Then the titanium plus aluminum giving TiAl3, and TiAl3 reacting with boron and giving TiB2, and this is titanium reacting with boron giving you TiB2. So, if you look at that, TiB2 is the lower free energy. So, as a result, if you put these two together, you can definitely get TiB2. That is what thermodynamics tells you. So, this is what people have done. What they have done is they made an aluminum titanium master alloy by reacting aluminum with K2TiF6 at certain temperature. This is 800 degrees for 60 minutes, and you end up in a composite like this. You can call it as a composite, you can call it as a master alloy, whatever you want to call it. It has a matrix aluminum plus particles. What are these particles? TiAl3 particles, because this is aluminum titanium alloy, and one can do X-ray diffraction, one can do EDAX. This is an example of the EDAX taken from one of these particles, and it shows aluminum plus Ta, and if we do quantitative analysis of this, you will see that it has 75% aluminum and 25% titanium. So, these are all TiAl3 particles, one can confirm this, and similarly one can take aluminum and react it with KBF4, and one can make aluminum boron, and these particles are AlB2, and one can do an X-ray, and you can see this is an X-ray of such a composite or a master alloy showing aluminum peaks and AlB2 peaks, saying that yes, this alloy has AlB2 plus aluminum. And now what you do, you take a mixture of these two fellows, the two master alloys, one is an aluminum titanium master alloy, aluminum boron master alloy, react them together at about 1200 degrees centigrade or 1000 degrees centigrade. A minimum of 1000 degrees is enough, is required for such a reaction, and you end up in TiB2 particles. And TiB2 is hexagonal crystal structure. So, one can easily see these particles with the growing on their basal planes. These particles, if you carefully see, all of them will have hexagonal morphology, and this is how they grow depending on the direction at which you cut the particular plate. The growth morphologies are almost like this, and one can generate the TiB2 particles of different morphologies depending on the temperature at which you make. And one can also do one thing, that take this composite and extract the particles out of the composite. How do you extract particles out of a composite? If you want to extract a particles, reinforcement particles out of the composite, what will you do? If you heat it, will they come out? Anybody who has been working to some extent on composites should know this. In any composites, if you want to extract the reinforcement particles, you have to dissolve the matrix. So, for example, in aluminum matrix composites, you can easily dissolve in aluminum in a sodium hydroxide solution. So, take a sodium hydroxide solution, put this composite into it, immediately aluminum dissolves and the particles will remain. And take all those particles and look at them in an SEM, you can see clearly all these disc shaped particles, okay, and this is the external morphology of these particles. And one can do an X-ray of these particles and show that these are only TiB2, nothing else, because now you will not get matrix peaks. Earlier, if you take the composite and do an X-ray, you will have the matrix peaks and also the particles peaks. Here you are doing only the particles, so you can see the particles peaks only will appear. So, all the peaks will be TiB2. This is how one can confirm whether there are also TiL3. The problem with this kind of composite making is that there is always a tendency for the formation of Al3Ti, because whenever you are making a composite, there is also aluminum liquid and titanium there. So, titanium and aluminum can react together and form Al3Ti. If you do not control your temperature and composition and time properly. So, as a result, you might end up in composites which contain both Al3Ti and TiB2, and Al3Ti is a more brittle phase because it has a body center tetragonal kind of structure. So, as a result, people want to avoid Al3Ti, and Al3Ti is much bigger particles, usually about 20 to 30 micron size, whereas the TiB2 particles, you can look at this. This is a 2 micron bar. So, the particles are of the order of 1 to 2 microns. So, very fine particles. So, one wants to achieve this kind of microstructure. So, which is possible only if you can suppress TiL3 formation. So, how to show TiL3 has been suppressed? By extracting these particles and doing X-ray, and to show that only TiB2 is there and there is no Al3Ti. If the particles also contain Al3Ti, then the X-ray will show the presence of those Al3Ti peaks. So, one can do like that, and one can show that these particles basically grow on the basal plane in a layered structure. And what is important to know is that these composites are more or less ductile. You can see the dimpled fracture that you see, that indicates that they are not only strong but also ductile, and you can see those TiB2 particles in those dimples. So, which clearly show that yes, one can have these composites with sufficient strength. We will talk about the strength a little later, and the ductility, and one can also make higher volume fraction of these particles. This is whatever I have shown you earlier was the 5%, this is with 10% volume fraction. People can also try higher up to 20% or so, and Again for this also one can make aluminum titanium, aluminum boron, mix them together and make a aluminum 10 TiB2 kind of composite. And this is the composites again, and this is the other route, which is what is called mixed salt route, where people add a mixture of the two salts. Whatever we have talked so far is what is called the master alloy route, where you separately make the aluminum titanium and aluminum boron, mix them together and make the final composite. Here what you can do is take liquid aluminum and add the K2TiF6 and KbF4 salts and finally get TiB2 particles out of it. One can also study this. We will talk about this in detail in the next class.